exclusive video educational platform. It is like no other, and it is going to be expanding massively here in 2025. Now, let's get into the day's lesson, and we're going to be talking commercial wiring, and we'll be talking branch circuits that evolve around commercial wiring. And again, there's going to be many videos that go into little details back and forth, but this is the first of the new generation of interactive videos. So let's get into it. All right, so commercial wiring, we're talking branch circuits today. What is our objective? Well, our objective after we work through this unit is we're going to be able to determine the number of branch circuits for a specific load. We're going to be looking and applying factors such as continuous, non-continuous. We'll talk about motors and how it would apply to heating loads. We're going to determine the correct rating of a branch circuit protective device. We're going to determine the preferred type of conductor for a branch circuit. And of course, we're going to determine the required number of size of conductors for a branch circuit in today's lesson. All right, so the first thing that we want to talk about is obviously what is a branch circuit? What makes up a branch circuit? Well, as you can see in the illustration here, we have the utility coming in right here. These are the service conductors. They hit this main disconnect, which is the main service disconnect in this case. And then you have on the load side of that, you have this feeder breaker. This feeder is feeding a remote distribution panel downstream. And it's being fed by feeders. And then, of course, in this case, it's a main lug only, as it's within the same building, and it's protected upstream in accordance with 4008.36. So all those rules are met. Now, here we have individual breakers, and these are feeding these circuits, conductors, out to specific loads, like an outlet or a receptacle that is mounted in an outlet box. And a receptacle is a device, but the branch circuit could be feeding a motor, whether it's cord and plug connected or hardwired, and the same for a heating circuit. Same scenario. Could be cord and plug heating appliance or hardwired. The main focus of us understanding what a branch circuit is in this layout is from right here. This is the last overcurrent protected device out to the outlet. Okay? Now, it is also extremely important for all of us to know that when we say outlet, we're not talking about the receptacle itself. Okay? We're talking about the point in the system where we take power from the system to supply utilization equipment. Now, it could be that the power from the building, the branch circuit, goes into a junction box, and then from that junction box, it supplies power to utilization equipment. Well, the outlet is the point where that power is taken from the building system to that utilization equipment. All of this is defined in Article 100 of the National Electrical Code. So we could have a box that we put a receptacle device in that something cord and plug connects to it. The outlet is the box where the device is mounted into it. Or it could be hardwired. So I could take this branch circuit, hit a junction box with a blank cover on it, and then out of it, I hardwire a whip over to a specific piece of utilization equipment. That is still an outlet. I think we use slang too much when we call receptacles outlets or plugs, but today we pretty much know all those things that we're talking about, but it's important that you understand the difference in what an outlet actually is, because it makes sense as we go through the NEC. You're going to see references to outlets like lighting outlets, which is basically the box that a luminaire would mount onto, okay? A receptacle outlet. It's a box where the power of the branch circuit's coming to, and you're actually connecting it to a device that you put in the box so that we can plug in attachment plugs to other types of appliances or utilization equipment. So it's so important to understand the different definitions, and I encourage everybody to take the time to really look at definitions in Article 100 and really get to understand them. And in our Fast Tracks program, we go over the different branch circuits, we go over the different definitions, and again, it's just a great way to learn the National Electrical Code. If you're interested in a great educational program, check out what we offer over on fasttracksystem.com. You see the URL right there. Check it out. We have something for you, whether it's grounding and bonding, or you want residential wiring, commercial wiring, or you're preparing for an electrical exam, we got that too in our Fast Tracks programs. So check us out on the website. Okay, so if we look at the definition in Article 100 for a branch circuit, here's what it says. It says the circuit conductors between the final overcurrent device, which is right here, this is the final, protecting the circuit, and the outlets. So you see right here, outlets, whether, again, as we said, whether it's hardwired or cord and plug, again, the outlet is where you would put the device in or you'd mount a luminaire to, for example. That is an example. But you could hardwire motors. You could hardwire other applications in following all the code rules. An appliance, you could hardwire an appliance. All those type of things. It's from the last overcurrent protection to the outlet. Again, whether it's cord and plug connected or hardwired there. That is what an outlet is, and that's what a branch circuit is. It's between the last overcurrent protection and the outlets, okay? So we're protecting these conductors with this overcurrent protective device right here, and it is the final overcurrent protective device. Now, there are different types of branch circuits that we need to be aware of. Whether you're in residential or in commercial, you're going to hear people talk about appliance branch circuits, general purpose branch circuits. What is an individual branch circuit? And of course, in commercial and industrial, we have a lot of what's called motor branch circuits that we have to be aware of. All of these branch circuits, again, have something in common. From the last overcurrent protected device out to the outlet is those conductors are branch circuit conductors. So let's look at each one of them. So what is an appliance branch circuit conductor? Well, a branch circuit that supplies energy to one or more outlets to which appliances are to be connected and that have no permanently connected luminaires that are part of the appliance, okay? So what we've got is, you've heard of small appliance branch circuits, okay? Required a minimum of 2 in that application in 210.11c, right? So those are appliance branch circuits. They're designed for appliances to be connected to those circuits, right? Next, you have the general purpose. General purpose is picking up things like you're going to have just a receptacle that an engineer adds in a hallway, let's say. Or maybe in residential, we talk about general purpose. It may be the receptacles in your bedroom, living room, things like that. They're just general purpose applications. And they typically are on with not only the branch circuit for the lighting, but also they have the receptacles, so you can have both of those on the same general purpose branch circuit. Now, one other thing that you might run into is an individual branch circuit. So whether it's an engineer design where they say, look, you're going to take a branch circuit specifically to a piece of equipment and nothing else can be supplied by it. Only that piece of utilization equipment, and that is it. Well, then that is an individual branch circuit. Now, people use the term dedicated branch circuit, but it's really called an individual branch circuit. And it's only to do what? It only supplies that one piece of utilization equipment. And it has to be installed in a way that it only supplies that one piece of utilization equipment. Let me give you an example. So let's say I had a requirement to have an individual branch circuit to a receptacle for whatever piece of equipment that's going to be dedicated to that receptacle, and the engineer specifies that. Well, if that's an individual branch circuit, we couldn't put a duplex in there because something else could be plugged into the other receptacle. If it's only for that piece of utilization equipment, whether it's cord and plug or hardwired, we have to do it in a way that that is the only piece of utilization equipment that can be connected to that individual branch circuit. So that's an important distinction to be aware of. Now, motor branch circuits, what are they? Well, they're the conductors, including the equipment between the motor branch circuit, short circuit, ground fault protected device, and the individual motor. Okay, so from the short circuit ground fault protection that is demanded by 430.52, okay, from there, all the way, and the components that are involved, all the way down to the individual motor, that is considered a motor branch circuit. And so again, that branch circuit is specifically for motors. So as you can see, we have certain branch circuits for appliances. We have certain branch circuits that are just general purpose, picking up receptacles and lighting. And then we also have individual branch circuits for specific utilization equipment. And then we have, of course, motor branch circuits. Now, that also brings us to a concept of what's called a multi-wire branch circuits. And there's people out there that literally don't like multi-wire branch circuits. But what are they? Well, in layman's terms, it's two hots that are sharing a neutral, so that there's 10 amps on one, a red, let's say, and there's 8 amps on the black conductor, and they're sharing a neutral, then only 2 amps will be present on the neutral. Now remember, this is specific to a multi-wire branch circuit. You could have applications in a three-phase situation where you wouldn't have a multi-wire branch circuit because the current wouldn't divide evenly onto the actual grounded neutral conductor. Okay, so again, this is talking about multi-wire branch circuit. And let's read what it says. It says, a multi-wire branch circuit can consist of 2 or more ungrounded conductors that have a voltage between them. Okay, good example is black and a red with the shared neutral. Between the black and the red is 240. Between the red and the white is going to be 120. Between the black and the white is 120. So they have a voltage between them, okay? But they also have a voltage between them and the grounded neutral conductor, okay? And it says it has a neutral that has a neutral conductor that has an equal voltage between it and each ungrounded conductor of the circuit, and that is connected to the neutral conductor in the system. Okay, so I have a system, let's say it is a 14-3 with a shared neutral, and I'm using it on an identified breaker with identified handle ties, so that ensures they're on different phases or different legs in the panel. So I've got 2 separate circuits, but it would be a multi-wire branch circuit. So like a 14-3 or 12-3 where you're sharing that neutral, this is a typical 122/40 volt setup. So it is, in our case, a grounded system. So it is a neutral, as well as being a grounded conductor. So I've got the black, I got the red, I install them on a 2-pole breaker, or I install them on 2 single poles with identified handle tie. I've got 2 separate circuits sharing that neutral. Well, that neutral is going to see the imbalance between both the red and the black conductor, which is on 2 separate legs. And it's important that you install it that way so that you don't get what's called a summation value. So in other words, if I didn't put it on a 2-pole breaker, or I didn't put it on 2 single pole breakers with an identified handle tie, and I just randomly placed them in the panel, if I accidentally or that I don't know what I'm doing when I'm doing the installation, and I put it on the same phase A, let's say, or leg 1 or leg A, however you want to call it, then what happens, it becomes summation. So if I'm pulling 8 amps on the black and 8 amps on the red, and I install it improperly, then what I could get is upwards of 18 amps traveling on the neutral. Well, remember, this was, let's say, a 14-2, it's good for 15 amps. Well, I got a problem. I'm pulling 8 on one, and I'm pulling 10 on the other, and typically the neutral would see the imbalance if we installed it correctly. But since we did not put it on a 2-pole breaker, or we did not put it on 2 single pole breakers with identified handle tie, if I didn't do that, I run the risk of now overloading the neutral, and that's a problem. And that is something we'll talk about in depth in a future multi-wire branch circuit, and we'll look at the problems, but we'll also look at the benefits of a multi-wire branch circuit. But anyway, I took you a little bit off of the topic, but let's get back to the lesson. All right. So you have appliance branch circuits, you have general purpose branch circuits, you have individual branch circuits, you have motor branch circuits, and of course you have a multi-wire branch circuit. Okay. Now, let's talk a little bit more about these branch circuits. The maximum continuous load on a circuit is limited by the rating of the overcurrent protective device. Okay, so for example, if I have a 120 volt branch circuit, this limits the non-continuous load to 120 volts times 20 amps to 2400 VA or 2400 watts. So that is the maximum that we could have on that circuit if it's non-continuous. Now, as you see up here, the maximum continuous load on a circuit is limited by the rating of the overcurrent device. So what is a continuous load? Well, don't worry. We're going to look at an understanding of a continuous load, but it's so important for people to realize that on a branch circuit, we could actually load that circuit all the way up to its wattage value or its VA value. If it's a 20 amp circuit, it's 120 volts, I can put 2400 VA on it or 2400 watts on it without any problem. That is non-continuous loads. If we know that the loads are going to be continuous, then we have to do something differently, okay? Because again, we wouldn't be able to get out the total 2400 VA out of it because of a continuous load. So we're going to have to limit it. And we do that with the overcurrent protector devices that we limit it. Okay, let's get back to look a little bit. Okay, so before we get into talking about continuous loads, let's go on and look at the scenario of how we would do this if we're looking for the general lighting. And again, we're talking commercial today. We're not talking residential, so we're just kind of keep it at that. If we have the general lighting, and then we'll look at what would be for the receptacle values that we got to work out, okay? And we'll show you how we incorporate the continuous loads versus the non-continuous loads so we make sure that we all understand what's going on here. All right, so the number. All right, let's start out with the general lighting. Again, we're doing commercial. We're not doing residential. So the general lighting loads for the feeder, we will use the factors in 220.42a. All right, so let's go to the NEC and look at that, and I will take you to 220.42. Oh, and by the way, we're in the 2023 edition of the NEC, so we want to make sure that we are going to be looking at that. So here we're at 220.42 of the NEC, and this is the link, by the way, okay, in case you're wondering. So in the general lighting part of it, or the lighting for the non-dwelling in 220.42, and you'll see from some people might remember this was back when it was 220.12. It is all kind of moved around, and here now it's in 220.42. And you'll look down here and you'll see that you have values down here. Let me make this larger. All right, a little bit bigger here. So what you see here is that you, depending on the type of occupancy you're dealing with, you have a certain value in VA, volt amperes per square foot. So, and this is for the general lighting. So if it was, for example, let's just look at, let's say it was this office right here. So we're looking at office. And so the general lighting would be, for this office, would be 1.3 VA per square foot of the office area. All right, and that is going to be for our calculation. We need to know what it is, okay? So let's kind of go back. But remember, we're doing what? We're doing branch circuits right now. Okay, so let's go back to the lesson and let's kind of get what we're working on. Okay, now what's the first thing that we need to do when we're determining the number of branch circuits, okay, that are going to be on the feeder panel, okay? We're not doing a service calculation. So the floor area, the floor area of a non-dwelling occupancy is determined by 220.5c as follows. So what does it say in 220.5c? It says the floor area for each floor shall be calculated from the outside dimensions of the building. Dwelling unit, we're not doing a dwelling unit right now, but the outside dimensions of the building or other area involved. Okay, so if we go look at the NEC, and we'll go real quick, go look at 220.5 so we can have context to it. And you notice this little note right here. That just means that this is new, so it's been relocated for the 2023. And this was all the information that we just read. And we get to ignore this part because we're not dealing with the dwelling unit in this example. It's just general rule when we're trying to find the square footage area of a building, even in a commercial, it is the outside dimensions of the building itself. Okay, so I wanted to make sure we were all there. So once you determine that, Then you simply will divide the number of amps by, for lighting by the size of the branch circuit over your current device for the lighting. But we have to get there first. So let's use an example. So let's say we were doing that office building. Okay, so the lighting. So let's kind of go back here. We want to do an example to get you on it. So here's that office building. Okay, right here. All right, and we said office building right here. And let me blow this back up for you. Okay, we're in the office building right here, and it's 1.3 VA for the lighting. Now, something is also interesting here. In the 2023 edition, if you go down here at the bottom, you will see there's a note right here. This note is extremely important because it already tells you that when you start to do this 1.3 VA per square foot that we're going to do for the office lighting, that it is already figured into that value as a continuous load. So you don't have to do anything else for it. You just take that 1.3. So let's just say we have a 50,000 square foot office building. That's its dimensions. And so it would be simply 50,000 times 1.3. And that is 65,000 VA. Okay, so again, let's just double check. 50 times 1.3 equals 65. Let's see here. Hold on. 50,000 times 1.3 again is 65,000. So we're going to write that down. Let's start. 65,000 VA is our lighting load here. Okay, and you're going to see some other tips that I tell you on this, but that's your lighting load. Okay. So that's what we got already factored in, already know what the loading is. We're good to go, okay? All right, let's get back to the lesson. Okay, so once we do that, we're gonna know what our value is. So next you just divide it. Okay, so we need to find out, okay, how many branch circuits